Good morning, everyone. Yay. So you can tweet or bleat or groan or whatever, film, I have no problem. I'm too old to worry about these things nowadays. Pterosaurs, of course, were filled with helium, which slightly undermines the results of the previous study, but there we go. And the other thing we learnt this week, sadly, was that pterosaurs also burn very well. I'm doing a butler. Right, pterosaurs. We've known about them for more than 200 years. The fossil record of their prenatal development, eggs and embryos, really only goes back about 14 or 15 years. We're very fortunate that that record is growing rapidly. We have some exceptionally well preserved, embryos and eggs, and I'll just point out a couple that will feature a lot. There's an ornithocheirid embryo from the Yixian Formation of China, which is just a tremendous specimen, and also there's a beautiful Pterosaur embryo from the Lower Cretaceous of Argentina. What we've been able to learn from these is quite a bit about the reproductive biology and the prenatal development of pterosaurs, which is some of it summarized in this sort of list here. The thing I want to focus on towards the end of this talk is the question of the supraprecocial flight ability of pterosaurs. Did they have it? What does it mean for parental care? This is a really important find, probably the best find in sort of this century so far for pterosaurs. This is a series of more than 300 eggs, at least 16 embryos, some bits of hatchlings, some juveniles, subadults and adults. They all come from the location of Hami in Xinjiang province in China. This is a Lower Cretaceous fluvio-lacustrine sequence. The critical thing really for this talk is that there are the three smallest individuals, embryos, 11, 12 and 13. That's what we're going to really focus on quite a bit here. They're really important in the context of what I want to say. They're all around about the same size, and they probably all belong to the same developmental stage. Now, Wang et al. And colleagues basically looked at these embryos and pointed out, they said that the forelimb elements, some of which I'm pointing to here, are less well ossified than the hind limb elements, which I'm also pointing out here. I'm not sure I can see that, but we'll go with it anyway, because what they claim was because those forelimb elements were relatively poorly ossified, it suggested that when the pterosaurs hatched out, as we see here, they could probably walk around on the ground, but they were not really ready to fly. In other words, no supraprecocial flight ability, and they needed to be looked after by the parents, which kind of contradicts the model that we've been steering towards for the last several years. So the big question really is, what is the stage of development of things like embryos 11, 12 and 13, or indeed these other embryos and sort of enclosing eggs here? You'll appreciate that you've got quite a little bit of time and development between an egg being laid and a hatchling coming out. So there's all sorts of stages of development in between. You understand that very well. We've kind of assumed on purely qualitative sort of assumptions and assertions that these things mainly are very late in terms of development, very late stage. But literally it's been assertions. And my colleague Charlie Dimmy and I have done exactly the same as everybody else and looked at specimens and said, yeah, it looks like a late stage embryo to me. But all our ideas about these prenatal development hinge on the correct identification of these embryos. And Charlie and I got quite concerned about this, so we decided we'd try and formalize the approach and try and be a lot more precise and accurate, and at least have some evidence to argue as to what status we thought embryos had. So we came up with which are complementary: egg shape, embryo morphometrics, a comparison of the degree of ossification of the skeleton within pterosaurs, and also a comparison with the very well understood stage developmental sequence in the alligator embryo. I'm going to go through those, more of an overview of each of these kind of the results that we got. First of all, egg shape. We're using at the moment a very simplistic approach, just comparing the length versus the width to get an elongation ratio. When we map it out, here's the elongation ratio down here. We're plotting that against predicted egg mass. We went into that in detail in the 2011 paper on Darwinopterus and its associated eggs, so I'm not going to repeat that here. What you are going to see is data for Hemipterus. Around about 38 eggs for which Wang et al. Provided in their data in their paper. The really interesting thing about this plot is that there's quite clearly a trend that you see here. And to pull that out, here's how eggs change in shape as they increase in size or rather mass. Bless you. Let's go back one. The smallest eggs here are relatively narrow and elongate. Those which we assume are around about halfway through development are somewhat more spherical, and the ones up here have the greatest degree of sphericity. And this sort of change in shape as we assume they get older, they sort of get fatter and rounder, is referred to technically as the Barrett effect. Oops. What you want to know is... I'm happy to be the model. So what we're actually looking at here is one of the smallest embryos from Hemi, and interestingly that sits inside an egg that's about halfway between the slimmest and the roundest. And the hatched egg from Hemi also fits somewhere up here with the more rounder specimens. There are two embryos, I've mentioned one already, from the Yixian Formation. These are ornithochirids. They are very, very closely related to Hemipterus from Hemi. These are, as I'll show you in a minute, a very late stage of development, and interestingly, they show the greatest degree of sphericity. So we have a very clear pattern emerging here, which is very, very encouraging. We were quite excited when we discovered this. There's more to say about it, but no time today. So ever onwards. Morphometrics, we've just been looking at this in a very simple fashion so far because data's limited. So the thing I'm just going to talk about is basically forelimb length, which is the sum of these four major elements. And what we did was just to take the basal element, the humerus, and divide that by the forelimb length to get a humerus forelimb ratio, which you see here. This is very unsophisticated stuff. And we plotted against forelimb as a measure of size, because size is what we were primarily interested in. We had a data set of, I was pushing on for about 100 specimens. That was all pterosaurs with a humerus of 20 millimeters or less in length. And that comes out to about 8 species. They are sitting here. What we see for some of those species where we actually have significant numbers, you will see, not surprisingly, a somewhat negative allometric relationship between the humerus and the forelimb. In other words, as the forelimb grows, the humerus takes up a smaller proportion. And if we add in lots more data, those trends continue. Now, the critical thing about this, and I should point out that the embryos are shown, there are very few embryos that we can do this with, but they're shown by these solid symbols. And they sit here. These are the two I've mentioned already. Interestingly, their proportions are comparable to those of, these are mostly juvenile pterosaurs, and might be the odd small adult amongst them. Really importantly here, though, here's Hemipterus embryo 13 and, of course, 11 and 12, and that sits over here. The hatchling specimen sits right over there. There is a big discrepancy in size between these, and that's really what I want to emphasize here. That's pushing on for about 75% larger in terms of the predicted forelimb length, which, relatively speaking, is about double the body mass. So it looks like these individuals here are at a substantially earlier stage of development than we previously thought. Right. More significantly, what we've also been doing is to look at the degree of development of the skeleton in the various embryos compared to a juvenile Pterodactylus. And we chose that one because it is most similar in terms of skeletal development to our embryos. If we'd taken an old adult, that makes life a lot more complicated. So what we did was to identify a series of skeletal units running from the beak end here through things like teeth and the actual skeleton, the limbs, all the way down to the foot over here. And we scored each of these. If it's blank, it means it didn't have it. If it's grey, it means, well, it was partially ossified, as we see with some of the bones here in embryo 12, but the diaphysis wasn't complete. But if the diaphysis was complete, as it is, for example, in the Pterodactylus cocci specimen, generally speaking, that was scored as black. We ignored epiphyses because their ossification and fusion generally occurs postnatally, and we're not so interested in that particular part of the process. So we scored up all our pterosaurs, and that included embryos here, and it includes some hatchling and juvenile specimens here. And the important point is, so there's Pterodactylus, it scores pretty much fully developed for all the units that we looked at. Critically, for our small embryos, 11, 12 and 13, they have the lowest degree of ossification. You see there are relatively few elements that are well ossified, there's lots that are partially ossified and lots that are just not there. What we also did was we combined the data for all three of those embryos to try to reduce any sort of taphonomic losses. Although for other reasons, ask me about later, we don't think there have been many taphonomic losses anyway, because it's actually quite hard to lose things out of eggs. And indeed, this one looks like it was pretty complete, and that's actually a CAT scan of an egg, so we're quite confident that what was there is indeed what was there when the animal died. Okay, moving on. The ornithocheiroid embryo from Yixian, that's much better ossified, as you can see. And finally, Pterodostro, that shows an even greater degree of ossification. So the message we're getting here is that these ones are less developed than this one, and this one's perhaps nearest to hatching. That's good. What we really need to do now is to compare it with something where we know what the stages of development are, because clearly in pterosaurs we're still finding our way. So we picked on the alligator, the main reason being that the alligator is the most closely related extant taxon. And you might say, well, hang on, you've got sort of crocodilians on one side and you have birds on the other. We looked at birds, but birds are so derived and their prenatal developmental sequences are so different from pterosaurs, it's very hard to see how we can make them work. Not that we haven't tried, and not that we won't continue to, but it's difficult. With alligator, it's much, much easier. And interestingly, the comparisons are very close. So what we have here is a same set of anatomical units, but in this case, they're arranged temporally. So you have 65 days of development for your alligator. Work by Mark Ferguson and Olivier Riepel has allowed us to sort of understand really well what goes on with them. The appearance, the ossification of elements in the skeleton are now staged very clearly. So, for example, at stage 22, which is around about halfway through, the coracoid starts to ossify and the teeth erupt. So we went back to our pterosaur embryos and asked the question, how do they compare? And again, we're looking at the hammy composite sort of data for the three embryos. And they come out at around about stage 22 or 23. They're actually, teeth are not erupted, they're missing several things here, ribs, gastralia, things like this. Yes, the phalanges in the wing finger are partially ossified and the metacarpuses, but we think that's related to development of the wing spar. So there's a slight asynchronicity compared to the alligator, and I might, if I have time, come back to that later. But overall, it seems to be at around about 22 or 23. Of course, you can see straight away that the ornithocheiroid embryo is somewhat further down the road. Okay, the gastralia are not present, but other things are, probably 24, and Pterodostro is doing really, really well, or perhaps sadly, this one seems to have died literally at the point when it had almost reached full development, certainly stage 25. These later stages don't involve the skeleton, so we can't really measure those, but that's the most developed one of all. What does all this mean, I hear you say? Please just summarize this for me. Okay, so here we go. Here's a map of prenatal development. Egg gets laid here, animal hatches here. We've arbitrarily divided prenatal up into early, mid, and late stage, and we've added hatching and immature just for the sake of completeness. You'll recall Darwinopterus, Mrs. T has 2 eggs associated with her, almost certainly at that stage of oviposition, so we have at least some idea of what eggs look like. Here are the hammy eggs in 3 stages of development. Here are the hammy embryos 11, 12, and 13, almost certainly at sort of middle stage of development. The ornithocheiroid embryos at a very late stage, which agrees with the sort of qualitative assertions we've all been making over the years. And interestingly, Pterodostro is about to hatch. And then, of course, we have 1 or 2 eggs from hammy that are thought to be eggs that embryos have hatched from. And finally, we've got pseudo-hatchlings and juveniles to compare with as well. This is lovely because it means that we have more data now to understand prenatal development, and there's lots we can do with this. No time to talk about all that today, but what we can focus in on is the hammy embryos 11, 12 and 13. And the reason this is important is you'll recall it was on the basis of these that people were arguing for an absence of flight ability. You can't, because this is only halfway through the stage of development. You can't really say anything about what's going on with hatchlings based on mid-stage development embryos. All they tell you about is prenatal development. They don't tell you anything useful directly about postnatal locomotory abilities. It's these embryos here, should you wish to use those, which do tell us about what's going on postnatally. And I think what they tell us is that, and I just want to say one thing, John's looming here, I'll have to spend more money now. The point I'd like to make here is that what we do see ossified, interestingly, are elements of the wing spars, both the fore and the hind limb, and also their proportions are similar to those of hatchlings and juveniles, which suggests that the unique pterosaur bow plan skeletally appears really, really early in prenatal development. We've looked at evidence before for precocial flight in pterosaurs. I talked about this in New York. There's lots of it. Clearly, they were precocial flyers. There's a very quick summary here. We do have, I think, an effective approach. We are expanding the pterosaur prenatal fossil record with that. We're seeing a lot more consistency within pterosaurs and compared to archosaurs in terms of the developmental patterns. And we remain committed to the idea that pterosaurs had supraprecocial flight with little or no parental care. So these beautiful illustrations, which are very evocative and engaging, sadly are almost certainly not true in our opinion. And the final slide you're all waiting for. So lots of people to thank here for access to specimens and also for talking about prenatal development in pterosaurs. And I'd also like to thank the deity that protects me from being poisoned by the mad chefs. Thank you very much.